Hey guys, welcome back to AlgoYogi. We're doing the tree series. Let's solve our next 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 problem, which is insert into a binary search tree. So let's go to the problem on LeetCode. The description is quite simple. You are given the root node of a binary search tree and a value to insert into the tree. Return the root node of the BST after the insertion. It is guaranteed that new value does not exist in the original BST, which makes our job kind of easier. So that if we come across a node that does not have any parents, we can just assign that value. Okay, now how are we going to do it? So let's see in the example here. First example says we have this binary search tree and the value we want to insert is 5. So the way we're going to approach it is, let's have an edge case first. If we're given an empty tree, then we're just gonna return 5 as a root value. Okay, so that's what we will do. Otherwise, what we're going to do, we'll check if my value is greater or lesser than my root node. So in this case it's greater, so we'll go to, sorry, it's in this way it's greater, so it has to be in the right of the binary search tree. Now we're gonna go to 7 and then we will check if we'll try to process it left. No, sorry, not left to right, but we will check if its value is greater or smaller than 5. So this is greater, that means what? It has to be on the left. So in order to place it on the left, we're gonna call it on the left, but the left is null, and we already gave an edge case that if the root is none, so basically we were trying to place it at this value. So if this is none, then we're gonna assign left node. We're gonna assign 7 left node with 5 as the value, which we have done already over here. If let's say this was like 8 or something, then in that case we will be assigning it over here. Okay, clear? We will be assigning it on the right side, because based on the value comparison with root and the value that we want to insert, we will be placing it at the right position. So it's a recursive version. I think it's quite simple to implement, and the reason is we are not doing any balancing or anything. Like a lot of time in binary search tree problems, or like when you create it, you basically assign it to the root value and send the current value to the rightmost value of the left, right? I think yes, rightmost value to the left. You wouldn't understand it unless we go to the actual implementation of binary search tree. So let's just go there later and solve this problem right now. Or maybe you already know. I know you guys are smart. So let's focus on the coding area. And so this is what we said: if root is none, then we return tree root, tree node, that's what it says, and the value that we need to insert. Elif root dot value is, it's never going to be equal, it's in the conditions it has given. So if it is greater than value, that means we have to place it on the left. So we're gonna call root dot left, and that would be just calling self dot on root dot left and value. Okay, elif root dot value, or I mean root dot write, not root dot write, root dot value is lesser than, and it's never going to be equal, so let's call it on the right subtree. Alright, awesome. Let's change this to right, this to right, and else we just return the root. I think we don't need to have the else condition, we already covered. If it's never going to be equal, either greater or lesser, and if the root is none, so then we just return the root. Okay, let's zoom out and try to run it on the examples. Awesome. The passing, and we can go over this again. So what's happening if, let's say, it was called on an empty tree, that means we are returning just making a root node of that value. Otherwise, if my value is basically had to be on the left side, which means it's smaller than my root, then I will call it on the left insert into BST, and I will assign whatever this will return me. This will return me a root after inserting it, right? Like, and this will keep calling until it reaches a null value where this value actually belongs. Okay, so, and it will keep doing these either of these two conditions until it reaches its right place to the very leaf node, wherever in left or right, accordingly it's calling on both sides. Just like on the first example, first it calls on 4 and it checks 4 is basically smaller than 5, then it goes to the right side, so this will get processed. Now it will call on right, which is 7, and will call on 5. So this time it will again basically check and it will basically call the left one, because now 7 is greater than 5. Then it will call on left is null, and because this is null, then to my left I am assigning this will return tree node as 5, so I'm assigning 5 here to 7. I think it's like really clear right there. Okay, and then finally I'm returning the root, so it will come back processing all those nodes from stack. So basically processing 7 and then processing 4, and then it will return the root. Okay, so let's submit this. Voila, 100%. Okay, time complexity, guys, would be big of log n, and because we are pruning it each time to get to the leaf node wherever that value belongs, and the way we are calculating is basically comparing to the root value. If it is greater than root value, we're going to the right. If it is lesser than the root value, then it belongs to the left. Okay, cheddar. Okay, then space complexity would be big of h, and that could be equal to log n in worst case. Okay, but actually worst case could be just big of n, actually. This is the best case scenario. If it is a perfectly balanced tree, then log n, of course. Otherwise h, let's call it h, height of the tree. Awesome. Let's go back to our AlgoYogi, guys. Make use of it, please, and let's mark it solved. See you in the next problem. Bye bye. Thank you. Namaste.